Hi, how's everybody doing today? Hope you guys don't mind if I walk around a little bit. I don't like to be too bound up behind that. So, real-world deployments, the SMPTE 2110, which only makes sense that my first case study is TR04. Sorry, I figured somebody's going to catch it, so I might as well put it out there. So when we've had customers come to us in these IP infrastructures, the big question that's always been asked is, I need to make a facility today that can handle 1080i or 720p, but I don't know what the future has. I don't know if I have to do 3G. I don't know if I have to do 12G. I don't know if I have to do HDR or HLG or PQ or whatnot. So every single one of our customers that have come to us today for an all IP facility from scratch has had that set of requirements. I need this today, and I don't know what I need in the future, so let's prepare for it. Well, okay, thanks for scoping that out nice and narrow for us. We appreciate that. This customer, by the way, this site's going live. It's here in the US, but because it's not live yet, we're under NDA, so I can't say who it is. So apologies for that ambiguity on my part. So what we run into in technology, what we've ran into in technology is the industry's changing very fast. Technology is moving at a pace that we in this industry have never had to deal with before. So this facility is going online here the next few weeks, but the implementation and design started 2 years ago. Now, having a 2-year design period from concept to design to integration to completion in 2 years, including building the building, is actually a pretty good period of time. But think about what technology has changed in 2 years. How many people here have a 2-year-old cell phone? Okay, really, guys? Come on. Anybody have a flip phone just so I can really pick on them a little bit? Yeah, I know, I saw one here somewhere. Yeah, exactly. But that's how fast the industry is changing. So 2 years ago, 2110 was not ratified at all. Now, we had TR03 as a concept, RFC 4175 and all that, but 2110 wasn't ratified. So the customer came to us with the requirement that we needed TR04 today, because they wanted the video with discrete audio, with the ability in the future to go to 2110. Okay, that's not too bad a requirement. And we already kind of talked about, in terms of signals and formats and stuff, they want to simplify the wiring. As little coax as they could do, as much single mode and multi-mode fiber as they can do. With our parent company being Belden, that's a win both ways around. We like that. And they wanted a top-of-rack end-of-row design, so distributed architecture. That was going to be really key for them. There we go. So what's the facility? 3 studios on multiple floors, and this is the interesting part. 2 years ago, they wanted as much IP at the edge as possible. What did that mean? Native IP. They didn't want to do a lot of conversion. Unfortunately, 2 years ago, there actually wasn't a lot of native IP devices. We had our cameras, there were some switchers and stuff around, but there wasn't a lot of servers that did TR04 or 2110. There wasn't a lot of graphics boxes that did it. There was hardly a lot of gear, especially compared to today's landscape where there is. So this site actually has a lot of gateway devices, SDI to IP and IP back to SDI. Traditional SDI switcher. Unfortunately, they didn't choose a Grass Valley switcher, which is all native IP. They went with another vendor that has to use edge cards. Very large multiviewer. And multiviewing becomes a really big issue in the IP domain because all the signals in your facility are now considered a function of bandwidth. It used to be a one-to-one relationship. I had an HD SDI, goes into a multiviewer, one-to-one, connector to process. Well, once we go to IP, we've removed the physical interface. So we've now become a function of bandwidth. So when you want to do a multiviewer that has 64 3-gig inputs, that's a lot of bandwidth. How do you provision that? Or how do you provision that same system to do 64 12-gig inputs? So these are some of the complicated questions we're having to address at this facility. They have master control and live production, typical TV station. Extensive IP and SDI connectivity we already touched on, but audio and video processing. How do you process natively in the IP domain? Everybody still needs to do up-down cross conversion. I think there's a few people in this room that can probably remember back when we went from analog to digital for a brief period of time, people are saying, hey, we're digital, we don't have to worry about reference now. Anybody remember that? Well, a few people thought the same thing on IP. It's actually even worse. So you still need to have frame syncs, you still need all the processing we traditionally have, just in the native IP domain. Remote production is a thing. We have the capabilities, they wanted to leverage it. So, first off, distributed IP infrastructures. We've been designing monolithic routers since the 1950s, where everything cables into one frame, and that one frame does all of your routing. Why would I want to use a monolithic frame in IP? Why use a 70-year-old technology in the IP domain? It makes no sense. So they wanted distributed IP infrastructure. They wanted a leaf spine, so leaves tucked around all over the facility, spine right in the middle, and that was their infrastructure. It spans multiple floors, again, reinforcing the need for distributed architecture. They also have multiple sites around the city. So it's not just they have their facility, their main core, but they have studios tucked around the city, and they had it all tied in over a bunch of 100 gig connections. So they wanted that to all look like one facility. They didn't want to say, oh, you know, I've got to tune in this live shot, or I've got to run this feed separate. To the operators, they wanted it to seem seamless as one facility. Also, they had uncompressed, you know, TRO4 feeds, and compressed J2K, H.264, MPEG-2, things like that, just traditional TV station stuff. This was the one goal the customer gave us. The users cannot know or care about the technology. That makes sense. If the operators have to know when they need a source that, you know what, this is a multicast source coming from a leaf spine that's actually about 3 kilometers down the road, let me get this multicast address, type this in, and we're good to go. It's not going to happen. So the goal was to have the users abstracted from the technology. We want the users to focus on creativity. We want the users to focus on making money. And if they're not making money, they're not doing their job. As an engineer and as a designer, if we're not allowing the station to do their job, create content, there's a problem. So that was one of the biggest challenges. How do you take new technology that hasn't been fielded too much in this scale and this size and make sure the users don't know? So since we don't want the users to care about technology, let's talk about technology, because we do. So talking about the rate of change, and this has been one of the large lessons learned from this facility. I don't know if everybody can see this. Apologies for it being a smaller graphic. So over the past 35 years, we've had 6 rates in terms of data. 10 megabit, 100 megabit, 1 gig, 10 gig, all the way up to 40 and 100. In the immediate future, we have 6 new rates happening today. And this kind of comes back to this accelerated pace of change. We have 2.5 gig native, 5 gig native, 25 gig, which is being deployed now, 50 gig, which goes to a new modulation technique called PAM4, 200 gig, and 400 gig. This is all happening today. So we're getting more data rates now than we have in the past 35 years. How do you design a facility to work with that? Well, there's some considerations. Just because you can go to higher data rates doesn't mean you have to, is the first part. Very much to this point. Those would be a fantastic 4th of July. Does not make our customers money. So what do? And this is one of the first lessons we learned from this facility. And this is a chart that we did internally showing the cost per link for a UHD signal. And what we found, that although 25 gig today makes for a very elegant solution, you can easily put 2 4Ks down 25 gig link. The cost per port is actually not that advantageous, because 25 gig is still expensive today. 25 gig 2 years ago was terribly expensive. So even though we had the ability to do 25 gig at the time, the cost was not enough to justify the expense. So that facility is actually based primarily off of 10 gig at the edge and 100 gig for the aggregate. You can still do UHD over 10 gig. Takes 2 ports. You can't do a single raster. But when their design consideration had to balance the value engineering of features over function and cost, it came to be that the 10 gig was the most cost advantageous model. Remember, this is 2 years ago. Today, it's different. Today, 25 gig is significantly cheaper. 50 gig, especially as a QSFP, is getting a lot cheaper. So although this chart made sense for this build, it doesn't necessarily make sense moving forward. And that's one of the first design considerations, is you have to consistently update your documentation and what you consider your business model for these designs, because the technology changes so fast now. So, another comic. We got to keep it somewhat interesting. How many people here have 3 different cell phone chargers in their bags? This isn't just our industry that has this problem. And remember, 2 years ago, we had Tier 03, we had Tier 04, we had SMPTE 21, or we had SMPTE 2022-6, and we had some other proprietary stuff by other vendors. 2 years ago, things were absolutely crazy. Thankfully, largely due to SMPTE, VSF, JT&M, AIMS, a lot of these groups have been able to coalesce and quickly ratify 2110, move that into the industry. So it's addressed some of the problem. So this is something that sometimes you don't know what problems exist because nobody's done this before. SMPTE has thankfully done a very good job addressing this issue, but it's been a big issue and this burned us. And in all fairness, and just complete openness, this burned us internal to just Grass Valley products. This isn't just an industry issue, this is a vendor issue too. That's SMPTE 2110-21. And what this basically comes down to is you have 2 main profiles we worry about, narrow and wide. And this really burned us at this facility. When a device is made out of an FPGA, so a card, a hardware card that fits in a frame, does one job. FPGAs are fantastic at doing one thing very well. And if you need to generate packets at exactly the right period of time and exactly spaced together, that's what FPGAs are fantastic at. So that's your narrow profile. And I know the gentleman from tech was talking about this a little bit earlier. So I'm definitely not going to go into the detail he did, but you can definitely tell because there's multiple people up here talking about it, it's an issue. So computers are awesome because they can do almost anything you ask them to do. Unfortunately, CPUs are actually pretty awful at doing everything because you have a scheduler. The CPUs say, I'm going to do this at this time, then I'm going to switch to this, then I'm going to switch to this, then I'm going to switch to this. So when you deal with a computer, a CPU-based device, say it's a server or a graphics box or a processing node that happens to be in CPU, the packets coming out of that box get really bursty. You get 4, 5, 6 packets all of a sudden, and then for a microsecond or so, it might pause, and then the CPU will do something else, and then it will send a few more packets, and then do something else and send packets. Well, I know the gentleman from tech had a slide showing what that bursty looks like. To the network, it looks like jitter. And although that does lead to a more inefficient network, it's not that critical until you realize that if you have a device that's wide, a CPU device, transmitting data to a receiver that's narrow. That narrow receiver is looking for packets at exactly the right time every time. And what happens when it doesn't get it every single time at the right time? What happens when you just send it 7 or 8 packets and it doesn't have any buffer? Well, it drops packets, it drops video. And traditionally in the IP stack, we'd just react and ask for the packet again. That's pretty awful in our industry because that takes away from the whole live video concept and it takes a lot more bandwidth. So in the early days, we didn't actually identify this as an issue because you don't know what you don't know. So we had actually purposely designed cards, and other vendors are doing this too, this isn't a Grass Valley plug, is we actually designed cards that are FPGA based, but they have memory on the front end. So now, if you do send 5, 6, 10, 15 packets to it as a burst, it'll cache it and then feed it into that FPGA at the right period of time. But if devices weren't built with that memory, you've got a pretty big problem. So now it's something that most of us know about, and if you look at SMPTE, it's part of the standard. So it's well known, but you have to know it when you're designing your facility. You have to identify what is a narrow sender, what is a wide sender, what is a narrow receiver, what is a wide receiver. Because it does have the effect on interoperability in your own plant. Just imagine the surprise that our guys had whenever we had a CPU device trying to go into an FPGA with no memory. We spent a day or two trying to figure out what's going on. Again, easily fixed, but you have to know it. The next part, and this is one that's been a pretty large issue in the industry, and another one that most people didn't understand at the time, is been addressed by SMPTE 2110-30, and it has to do with packet timing. And when you send audio out in 2110-30, it's almost always in trunks. It might be a 4-channel trunk, or an 8-channel trunk, or a 16-channel trunk. It's rarely a mono, but it's doable. So when you send stuff out in trunks, you have a finite amount of packet, 1440, that kind of stuff in packet sizes. So if I send a packet out every millisecond, and I'm trying to fit 16 channels of audio in that packet, it's not going to work. It's going to be too big, Switch won't let it pass. So SMPTE has these different levels of packet timings, A, B, and C. So what we discovered at this facility, and again, SMPTE did a very good job catching this, is they said every device shall support level A. Meaning every device shall support 48K from 1 to 8 channels at packet times of 1 millisecond. Fine. But what happens when I want to send 16 channels down a trunk? Or more, because you can. So now you have to go to level B or level C. So now with B and C, I can do 1 to 8 channels on B at 125, or on C, I can do much more, up to 64. So if you have a device that's sending out 16 channels of level C, but your receiver is level A only, you got a problem. This became an interoperability issue. Just because the devices can all support and have to support A, doesn't mean the workflow allows everything to work for A. So what we found is a lot of older audio consoles and a lot of older intercoms that used to do AES 67 or other standards that have been put into the 2110-30 domain have this problem. So it's a part that had to be identified, and identified rather quickly, because when you design the facility, you have to pick out that time. Am I going to do 1 millisecond? Am I going to do 125 microseconds? And how many channels of audio am I going to do? This facility chose to do 16-channel audio trunks. So for every video they had, they created one video IP stream and one 16-channel audio stream. A lot of customers are now saying, I want four channel streams. Gives you compatibility and gives you some granularity for the ability to mix and match the audio. So again, it's an interop part SMPTE took care of, but when you design the facilities, you have to be weary of it. Which brings us to the next part. We've found that if you really want this to succeed in an industry that is changing as fast as it is, any hardware you have, especially FPGA-based devices, need to be firmware upgradable. You know, this facility launched TR04. With the firmware update, they can switch to 2110. You just got to make sure that if that is in your roadmap, if you think technology is going to change, it will, and you need a product to support it, it needs to have a firmware upgradable. Now, the important part is it has to be field upgradable. If you have your entire infrastructure is based off of FPGA cards, you don't have to pull every one of them out while you're on the air, send it back, have them update it, send it back to you. It's awful. And so you want to make it easy, and you want to be able to make it so the customer can do it themselves. Now, this doesn't affect transport stream. This isn't just a TR04 2110, but third-party device control. ISO 4 and ISO 5 really wasn't on the radar when this facility came around, but we still need to support it. If you find a vendor that only supports their protocol and has no willingness and adopting an open standard like ISO 4 and ISO 5, that's going to be a problem. Well, again, 2 years ago, ISO 5 didn't exist. ISO 4 was kind of coming around. So having a firmware updatable device to support newer control topologies is really important. So next up, we had a lot of lessons learned on the network switches. The first site we did for our first large IP deployment was actually a truck. And it was a truck in the UK. And that site, we went with a switch that the vendor said will work. You know what, you need 10 gig ports on all the edge, you need 40 gig uplinks, we'll support it. Well, we put it in, started wiring it up, all the cameras came in, switch load 20, 30% fine. We put in servers, switch load got up to 40, 50% fine. We brought on the switcher, the actual video switcher, not the network switch, brought on the video switcher. All of a sudden, our network hit 60% and then it went to 0. Dead. Well, that's a problem. Well, in a few slides, not to do too much of a teaser, we're going to kind of address what problem we had. So on this facility here, this is not the truck, this is a larger facility. And again, I'm sorry that the people in the back may not be able to read all of this. This is the high-level diagram. And one thing about this facility is we're doing a leaf spine architecture. There wasn't, at the time, a spine large enough to handle all the bandwidth we needed. So what you actually see here is this is a SMPTE 2022-7 facility. So you have an entire X network and a complete mirrored Y network. You have 2 spines, so it's a multi-spine, and you have 11 leafs. So again, it's completely mirrored between the two. So that's the media network, multi-leaf, multi-spine. There's a separate network that doesn't require the bandwidth of the QoS that the media has. That is our standard broadcast LAN. This is what we've always had for command and control and configuration and all that kind of stuff. And then you see stuff like this is a Cisco facility, so the Cisco DCNM and the Grass Valley SDN management system and the PTP and so forth. So this is where the whole SDN infrastructure really comes important. If you just bring a facility up on one switch, maybe a very small truck or a very, very small call letter, the level of interaction with the SDN system is actually pretty low. But once you start doing multi-spine, multi-leaf, now you have to do a lot of bandwidth management between all of the spines and all of your leafs. Because what you don't want is a blocking architecture. If the customer says, I need this source to this destination, take, and the control system says, hey, sorry, we don't have enough bandwidth, and it's a news feed during a police chase, this goes back to the whole the users cannot know about the technology thing. So it's very important to make sure that your system has been architected to mean non-blocking. This is a little bit of a deeper dive on just one of the sides. This is, again, X and Y sides are completely identical. So we're seeing both spines across the top, and now we're seeing all the multiple leafs and how we break it down into gateway cards, direct IP devices, and so forth. And this is actually a pretty elegant design. I can't take any credit for it. This was actually done by the integrator and and Cisco. So we can't take any kind of credit for the leaf spine architecture. But the important part is we got the 11 leafs, 150 IPGs. So those are our IP to SDI converters. So that's quite a bit of IP conversion. Native IP cameras, native IP multiviewers feeding off the multi-spine. So this is a pretty good scaled system. This system is roughly 1,000 inputs and 2,000 outputs. With technology today, we're able to push about 35,000 squared. We couldn't do that 2 years ago. So back to the original thing, I was talking about how not all switches are the same. This right here is in SMPTE 2110 a breakdown of what one signal conversion would be. This is one SDI to IP conversion. SDI comes in. We have one IP address for the SMPTE 2110-20 video, and each of the audios is 4 channels. So we get four 4-channel audios. And then we have your 2110-40 for metadata. So for every single input to that system, you have 6 IP addresses on multicast. And they're all different data rates. If everything, like in 2022-6, everything's going to be fixed at 1.5 gig or 3 gig, and that's it. But the video is, based on the weight on -20, it's actually only the active components. So, what used to be 1.5 gig now could be 800, 900 megabit or 1 gigabit. Audio, you can usually expect about 1.5 megabit per second per AES channel. So you're talking 6 megabits per AES stream. And metadata is low, it's almost a rounding error. So now we have to build a system that's leaf spine with aggregated data across the entire facility and across the entire city, but guarantee that all of this bandwidth can get to any source, to any destination, at any time, non-blocking. It's a lot harder once you start doing multiple data rates. And that's where some of our switches in the early days would fail. Again, we didn't have the problem at this project because we already had the troubles at the truck I was talking about. What had happened on that truck is once that switch hit about 60%, there was not enough bandwidth in the backplane on the ASICs and on their FPGAs to guarantee that every packet source can go to any destination at any time, because traditionally it's just been doing email. It's just been doing stuff where we can apply QoS and things where we can apply statistical multiplexing. Well, when you want a true non-blocking system, you can't do QoS. Because once things start to queue up, cool, what's more important, audio or video? Which one do you want? I don't want to make that call. So you have to architect it so that it's not blocking across all components, audio, video, and metadata. So you have to find and you have to work with your switch manufacturer to select and test. And this is the really important part. Test before you deploy. That the infrastructure can support entirely non-blocking bandwidths. If you're going to put a 10 gig port, you want to be able to load that 10 gig port to 9 gig. And you want to deploy that across the entire system. So having a partner with a Cisco or Arista or Mellanox or whoever your switch manufacturer is going to be really important. Because you're going to be able to test it and validate it and move it forward. It gets even more complicated once you start adding things like SMPTE 2022-2, compressed feeds, even lower data rates or variable data rates. It's all something you have to kind of keep in your mind. Now, PTP. PTP is something that all of us just were kind of like, it's reference. I think there's more of the few of us people in this room who've worked together on PTP projects over the past couple years. PTP has actually been the most frustrating part of deploying IP. Yeah, see, there's a couple of us who've all worked together on projects. We learned this one really rough. First off, picking your grandmaster clock is very important. Most grandmaster clocks you'll find from broadcast vendors give you one 1 gig port. Cool, that should work, right? Well, when the switches you're plugging into only support 10 gig, 100 gig, and 25 gig, well, you got a problem. How do you convert? Second, if you want your PTP to feed multiple networks, how do you do it? Remember, this is all XY. So we have 2 networks to feed off base requirements alone. You've got 1 port. How do you duplicate it? So at this facility, and I don't want to say this is how to not do PTP, because this actually works quite well, but it's not a very efficient design. So that we had to put in extra switches just to distribute the PTP. So it was a little overly complicated in my opinion, but again, fully functional, and you don't know what you don't know until you do it. So for a drawing that probably nobody can see, apologies, what we have here is we have our PTP core, we have our XY media networks, and we have the broadcast LAN. So for this system to work, we needed 6 PTP links. But again, the PTP generators only have 1. That's a problem. So how do we get around it? We put a set of switches in this case some Cisco's, that had 1 gig on the edge, 10 gig on the aggregation, and that was our converter and our distribution for PTP. Pro, it works, always a pro. Con, that's an additional set of switches you now have to maintain, and if there's a problem in the network, you have to diagnose, and that your staff has to know about. You know, the 3 a.m. engineer, who is a fantastic SDI engineer, if he loses reference and he's by himself, and it's because one of these switches died, what is the probability of him very quickly finding that is if he doesn't have the experience or the knowledge? Now take that and scale it down to a small market where there's not even an engineer. So having a PTP system that is simple as you possibly can make it is really, really important. One thing that was a very good design that they did is they had the multiple clocks feeding multiple switches, and they had multiple entry points into the media network. You never want to have a single point of failure. If you run all your PTP into one switch, and that one switch dies, it doesn't matter how many grandmasters you have, you just lost them all. So they're actually quite smart, and they ran it into multiple leafs to get it into the network. But this introduces a problem. So what if a grandmaster dies, or both grandmaster dies? It's a Cisco switch, so Cisco switches use boundary clocks, which means the switch is going to generate its own time, and it's going to distribute that out to all the slaves. You lose a grandmaster, it's fine. These 2 switches at the top start generating their own clocks. Well, to my knowledge, and if there's anybody from Cisco here to correct me, there's not a cesium atom clock in the Cisco switches. It's not near as accurate as what you're going to get from the GPS. So when you bring your grandmasters back on, there is the real possibility that you've had clock drift. So now what? You do a jam? Sure, it's just going to make every single device on your system hate you, but that's what you may have to do. So it brings up questions. How do you resync the clocks after a failure? So architecting PTP for having no single points of failure and addressing the issues that boundary clock does bring is really important. And this is one of the more annoying parts of this facility. And this is all facilities, and this isn't going to change. SFPs are expensive and add complexity. I was really glad to see the gentleman before me had a whole part of his slide presentation on monitoring SFP and SFP health. 10 gigs are cheap, 25 gigs are more expensive, 100 gig single mode SFP is about $60,000. So you see that they range greatly in price, and they range greatly in functionality, but you have to monitor every single one of them. If you have an SFP die on a 2022.7 network, you're not going to have any degradation until that second SFP dies. So you have to know the health and status of every single stinking SFP in the system. So there's a couple options. You can natively run everything on an SFP, or you can aggregate, but it has a big effect on failure impact. So this is not a facility, this is just a theoretical exercise. 288 squared SDI to IP conversion, non-aggregated. This is just using cards to convert SDI to IP and IP back to SDI. If one card fails, that actually has very little impact on the facility. I come from the Envision side, because Grass Valley's a bunch of companies together now. I come from the Envision side. And the best we can ever hope for in a baseband router was a 9-in, 9-out failure block, meaning if a card died, you can lose 9 in or you can lose 9 out. That's the biggest failure you can have. Using IPs off of this technology, we have a better failure block than any SDI router ever made, meaning it's a more adaptable and more block failure resistant design. Downside, you have to maintain all these SFPs, all these cards, and all the maintenance. So how about you aggregate it? Let's bring it into one box and aggregate the whole thing. Well, we can do that too. Makes the wiring much more simple. Makes maintenance a lot more simple because you have a lot of SFPs to worry about. But as a design engineer, I'm starting to have considerations on impact block. What happens if I lose a box? Instead of losing 5x5 or 8x8 or 9x9, now I'm losing 144x144. So these are all design considerations. I'm not saying which one's right, because what we're finding is a combination of both is right. And that's something to be considered when you do the designs. So you have to ask yourself a lot of questions at the very start. And these things kind of keep going, getting more and more complex as we're learning more and more. First off, you have to ask yourself, what standards do you want to do? Or do you care? If you consider a standard of video and audio is really just a reflection of bandwidth on a system, do you care? But you have to identify it. How much IP conversion do you have to do? How much MADI, how much audio conversion do you have to do? What devices are native IP? What's the amount of them? What's the format? What's the control? If it's native IP, it only does SMPTE 2110-30 level A, but if the rest of your facility is C, you got a problem. So you just have to be very careful when you design this and identify the capabilities of every device on the system. Multi-viewers is a whole session on itself, so we're going to skip by that one. Connectivity matters. We've already talked about it. It's a very big, important part. Control and monitoring is the most important part. As much as SMPTE's put the time into 2110, 2110 is a transport stream. That's it. It's a way of getting bits from point A to point B, but it doesn't have the control. It doesn't have the workflow. It doesn't have the engine to drive the creative cycles. So control becomes massively important. Timing. You may have some legacy devices. They're only blackburst. If you have a server from 5 years ago, it doesn't even know what PTP is. So how do you combine PTP and blackburst in the same facility and make sure they're on the same time domain? All considerations for building out. And system redundancy. And this is the one that it's definitely a discussion for a later time and something you guys can think about. Is when we did this site, we did a full XY network, full SMPTE 2022-7 redundancy. Every source fed 2 switches. Every destination received from 2 switches. If you talk to the engineers that did this project, they said, we really spent a ton of money to make the entire facility completely redundant. The reality is, we probably could have valued engineered that a little more. So if you have the budget, by all means, do the redundancy. But value engineering does have its place, where you back up the feeds that make you money, but things that are superfluous, like, do you really need to back up the multi-viewer feed that feeds the general manager's office in a TV station? Probably not. And you can actually select a lot of sources and destinations that don't need an ultimate flexibility and ultimate redundancy and move forward. So that brings me to my last part, and in my opinion, this is the most important part we've learned. Right? Yeah, let's just restart it. Hey, it's 3 o'clock in the morning, or actually, it's the Super Bowl. Our network switch just took a dump, so let's reboot it in the middle of the Super Bowl, right? Yeah. In that case, I really hope you have SMPTE 2022-7 redundancy. But this also talks a lot about what the engineers have to deal with today. Engineers have to deal with the fact that they have to understand SDI. They have to deal with the time-sensitive nature of our industry. And they have all the pesky things we've always had to deal with. Health and status of devices, health and status of SFPs, power supplies, fans. And now bandwidth becomes an issue. Do I have enough upstream or downstream bandwidth? If an SFP fails, what's the impact on my system for bandwidth allocation? What's the health of my ports? What's the switch load? What's my media flow doing on the multicast? You know, am I having IGMP problems? Am I having media flow access problems? How many people in here have their entire engineering staff today that is up to speed on IGMP and multicast, unicast media flows through a diversified leaf and spine network? Every engineer. Nobody? It's not to say that's not the problem now, that will be in the future. Not every engineer has to understand the intricate details of the facility, but they have to know enough to reach out to the people who do and then get that ball moving. So engineering training is becoming a really big issue. So if you guys move to IP, how many more engineers are you going to hire to support it? Okay, contract possibly. Yeah, exactly. Check the 401k because, you know, I got 2 or 3 years left, right? The reality is they're absolutely not hiring more staff. So the engineers have a much larger burden to bear. The engineers now not only have to understand everything about the SDI world and the traditional digital world, but now there's the IT side too. So having a centralized interface for all this information, what is the health and status of my system that I can sit down quickly and figure out? That's really important. I need the ability to show data that's pertinent to the operation of the network while it's in a nominal state. If everything's fine, do I need the health and status of every SFP in my system? No. If things break, I need to know really quick what's abnormal. So having that unified tool that allows people who don't know everything about everything to simply sit down and quickly diagnose the system and turf that off to other things. So this is my last slide, and this is my last big ask, is engineering training is more important now than it's ever been. Engineers now have to understand everything we've always had to know about SDI and blackburst reference and even analog and RF. But now, they need to know about switch configuration, switch topology, flow controls, SDN, IGMP, SMPTE 2110, PTP 2059, SMPTE 2022.6. I can just sit here for the next 5 minutes writing off standards and functionalities our engineers need to know. My ask is, for everybody in this room that's either an engineer or a manager of engineers, take the time now and start training the engineers, start training the operators, send them to get a Cisco CCNA or an Arista certification or a Mellanox thing. Spend the time, spend the money now, because it's not that much money. The engineers will appreciate it because you're valuing them. You're showing that I'm interested in their success. But if we want to just talk about money, it's a whole lot cheaper to train an engineer to fix a problem than to do a whole bunch of make goods during the Super Bowl. So it's well worth their time. So thank you. That's all I got.
All right, Rob, if you could stay up here for a few minutes and we can encourage Thomas and the two Carls and Henry and Amar and, of course, John Mayotte to come back up to help facilitate our Q&A for the entire super session. That would be great.